Chapter 6, Matrices, plural matrices, singular matrix. A matrix, you actually have met an idea of a matrix because a vector, a two-dimensional vector, is an example of a matrix. So, for example, a vector 1 right 2 up is in a matrix form. Okay, what it is, it's simply like a table of values. It's got to be a rectangular one, so you have to have a number of columns and a number of rows. Okay, if you have got a matrix with some given, then you can also talk about its size. So if you have n rows and m columns, then this matrix would be n by m size. Okay, where n gives you the number of rows and m gives you the number of columns in that order. Let's just go through few definitions or ideas. So what is a square matrix? So this is something that obviously arranged in a square, so the number of columns is the same as the number of rows. So your n would be equal to m, so like 2 by 2 or 3 by 3. Okay, and actually 2 by 2 and 3 by 3 are matrices that work either in 2 dimensions for 2 by 2 or 3 dimensions for 3 by 3. A zero matrix, so it's actually and each entry in the, let me just actually mention that each entry is called an element. There you go. So if all the elements are 0, then the zero matrix is going to be 0. Okay, you could put it in brackets as well, but this one is 1 by 1. Identity matrix. Identity matrix acts like 1 in multiplication. Okay, so it's a matrix that you can use to multiply another matrix by, and it will leave it unchanged. That's the definition of identity. 0 is an identity in adding. So like if you add 0 to a number, it leaves it unchanged. So 0 in addition is an identity. But 1, and for example in 2 by 2 matrix, so in 2 dimensions, this would be identity matrix, so we call it I. Okay, and 3 by 3, you will have all zeros apart from the diagonal, going from the top left to the bottom right. Okay, so this is the identity matrix, very, very important matrix. Now, a little bit about notation. We use capital letters. In text, they will be bold. All you need to do, if it's matrix M, you will use capital M. Matrix B, capital B. That's it, I think, for now. So let's see whether we can do example 1. So example really starts easily. Looking at these 4 examples, can we identify the size of each of those matrices? So this one here, you've got 2 rows, 2 columns, so the size is 2 by 2. I suppose if you wrote by 2, that would be okay as well. This one here, you've got 1 row and 1, 2, 3 columns, so the size is 1 by 3. This one, 2 rows and 1 column, so it's 2 by 1. And this one, 1, 2, 3 by 2, so it's 3 by 2. Very quickly. Okay, when you can add matrices, but clearly when you add matrices, they need to be of the same size, okay? Because you will be adding the corresponding entries, so elements, to each other. So, or subtracting. This is called conformable, additively conformable. Okay, so let's have a look at example 2. we're going to add these two matrices, and really this is very intuitive. You've got to find the corresponding elements and add them together. So 2 will be added to minus 1, minus 1 here will be added to 4, then you've got 0 will be added to 5, and 3 will be added to 3. So you'll write it the long way, but anything that's simple, you could just do it quicker. Minus 1 add 4, 0 add 5, and 3 add 3. If you're doing this, make sure that you don't get muddled up in, don't write those entries too close together. Maybe do even a little tiny sort of separation here. But just make it clear where each entry starts, where it finishes. So it's 1, 5, 3, and 6. Okay, so let's do this one a bit quicker. 1 take away 0, the top left entry is 1. Minus 3 take away 2, minus 5. 4 take away 1 is 3. 2 take away 5 is minus 3. 1 take away 2 is minus 1. 1 take away 3 is minus 2. There you go. Okay. So let's look at the how to multiply by a scalar. So really just by a number. Okay. And you've done that with vectors. You've multiplied vectors by 2, and what effectively happened? You have doubled both numbers are going across and the number going vertically. So this is exactly the same idea. So multiplying by 2, by the way, a word scalar refers to a number, a constant. So like 2, 3, pi, you could call it a k, when meaning that k is a constant as well. So here we just need to put 2 lots of 1, minus 1, 2, 0. That tells me that I've got 2 of everything. So 2 times 1 is 2, 2 times 2 is 4, minus 2 and 0. Okay, half of B is a half of my matrix B. So we need to halve each of those. So it's 3, 0, minus 2. Okay, now why can't we find A plus B? Because they are not of the same size. So they are not of the same size. You could say not additively conformable. I'm sure I'm saying it wrong. Not additively conformable. Okay, so let's have a look at example 4, and then you'll be ready to do exercise 6a. So here we've been told that if you do A plus 2B, you will be getting matrix C. And using this information, can we find what A, B, and C are? That's little a, little b, and little c. So it's like a puzzle. Let's substitute those matrices into this identity. So it's A, 1, 0, 2. Add 2 lots of 1, 0, B, 3, which is matrix B. That must be equivalent to matrix C. There you go. So if we do if we compare the top left entries, you'll be getting A plus 2, because 2 lots of 1, that's got to be equal to 6. Okay, so what I've done here is taken that A, and then I've done this, and then made it equal to that. Okay, so that gives me A is equal to 4. Okay, talking about the top right, you're going to get 0, add 2B, and that is equal to 6. So B is equal to 3. Bottom left will not generate anything. Just to show you, you have 1 plus 0 is equal to 1. So, you know, it has to be. Maybe you always need to consider it just to check whether that will work, but it does. 2 for the last entry, add 2 times 3, which is 6. is equal to C, so C must be equal to 8. Okay, so off you go, start exercise 6A.